Okay, now we are going to start lab lecture 5, part 2. Until now, we cover initiative steps, step 1 and step 2. We are going to dive into step 3, load data into a Spark data abstraction. So in this part, we load our data, which is initiating our logical plan. And prepare data for this operation. There is a two operation. Transformation means silent operation. This is moving operation, executed operation. So prepare data for some action on data. Because you remember, we have a data plus algorithm plus, that human decision making. So this is algorithm, transformation and action is here. And data part like data initiating, initializing, setuping, data modeling and schema defining. After that, data abstraction. Then we need to come to the algorithm. So data can be, loaded because it's a big data from the CSV, JSON file, Parquet, HDFS means Hadoop, distributed file system, S3, RDD data, whatever. This data come into this tree. This is not the data format. This is the abstraction. Is a ready to manage data framework. After organized data, we need some controlling data in the memory. So we need now, let's come back to our main scenario. We need to load sale data for analyzing across two clusters, in NA data center and EU data center. So imagine loading sale data from distributed data center, like North American, Handel, USA, and we are going to load data. This sales data is analyzed to calculate average sales per product category using efficient processing. So now we have, again, three methods to load data. One is the RDD, one is the DataFrame is a blue, one is the dataset. So let's quickly look at that one. In the RDD, because it's a raw data and parse to structure, this is the unstructured data. So you will parse context to text file, and then you extract the header. Then you need to load for example, our data is the CSV data. This CSV data will be map. Do you remember map reduce? And it will be, read file and split by virgule on the text file. And this will be preparation in RDD. In the, CSV, we already did this part for, data model. Then we need to load a Spark simply, because this is the data frame, is easiest one. Just a Spark read CSV, header true, and schema. We already defined the schema because we already defined our schema. We are saying to the Spark that we already have, don't use predefined schema, use my schema. And then just for sample, because data is more than 500,000 record, we will show 5, you can show 10, whatever. And for dataset, we need to, here we need to, little bit complicated, we need to, define the name tuple, we already did this is the schema part. Loading is somehow similar. So we need to convert data. Until here is a data frame, similar. Here data, this is a schema different. This is the loading data frame. We need to convert data frame to data set. So we need to map and bring to the data set. So we don't need to go for this one. So we will go for this. We already have this one. We just need to load the data. if I run this cell, what would be happen? Can you please pause video and tell me? Yes, you are right. It will be error because path not defined, either defined from Google Drive or should be in the Google Colab. So if Google Colab should be data here, this is by default exist, right? This is by default. You need to put your data here. So you need just press this one and go to your data. You already download from that Kaggle website. So your data is here now. So if I run, you know, this is now loading, is very big data. Okay, loading finish. Then just simply I read that one shows 5. Now successfully will shows yes. You can put 20 because just so data load with this message we will make sure that successfully everything done during the process. We can also use other sort of JSON. We can use load JSON file. Let me show you the code. So if our data is not a CSV data, we can use give the path, and then instead of CSV here, Spark reads same dot JSON instead of CSV. And if the Parquet data, here we use Parquet. Or if there is a HDFS, we need give the HDFS path and then read the data. CSV, which is inside HDFS, remember Hadoop. Or if S3 format, you need to, your data through the S3, you need to give S3 path. This can be one example, which your data, CSV data, if you already install S3 or for the HDFS, you can read simply from that one. So, if we use DataFrame, you are working with a structure and semi-structured data like CSV data, and will be better performance, and operation is like SQL-like operation. But if we use the RDD, it is for unstructured data, low level. We can control data in detail. Is low level programming, and many settings we need to do manually. And for dataset, already mentioned like type safety, and you need to combining benefit of the RDD and data frame. So let's go. Next step 4, partitioning in Spark data abstraction. Okay, step 4, partitioning in the Spark data abstraction. When we finished 3 steps, now in step 4, we are going to partition our data inside a driver as well as a process inside cluster. So partitioning is very important in Spark, and let us to do distributing processing through the multiple node inside the cluster, one data center, maybe several nodes and tasks. So partitioning is the logical division. Data will be divided to a smaller and manageable chunk that it is called partition. That is good for increasing the efficient processing. So usually we can do partition, but there is a possibility to do default partitioning. Spark automatically determined a number of partition based on the size and cluster configuration. Usually one partition per HDFS block divided by every around 128 megabytes. For instance, we have a 500 megabyte, it will be divided to 4 or 3 partition automatically based on the size. So we can, when we want to do partitioning, we should look at our data. In our data, country and stock code is good to partition. It is good data to divide data logically. So we need to find in our data proper field which we can divide. So for our real example, which is North American data center, so we will consider two partition for USA and Canada, and European we consider one partition for UK and France and the other for other European country. So within each cluster, data is divided to partition that help for the partitioning process. So more partition allow better utilization. So if a cluster has a 4 core, 4 partition ensure all core are utilized. So the core, as you remember, we said the number of core double would be number of partition. Minimum is the equal. So it is good for fault tolerance. If one task fail inside the cluster, only corresponding partition will be stopped. The other entire dataset would be safe. Flexibility and scaling. So you can play work process with a long big data easily. So in our case, partitioning, we will do 4 partition. As I mentioned, this is based on the country, and based on the range, which based on the stock code. This is based on the country field. We decided to do this one. So we will show how in the code we will divide this stock code based on this number. So if we go for RDD, because we are not going to touch RDD, because RDD is for unstructured data. Just if you look at that one, simply here is the loading, here is the load data set, and parse the CSV data if we go for RDD. Partition by country, simply we RDD parse, which is here, filter based on the country, and we define 4. So for country, we will say 4 partition, and then we print it. Based on the range, then we need to assign partition based on the stock code rows. So you remember we defined rows 1, rows 2, rows 3. So for all rows, because it was no schema, we defined it. So we will say from this less than, for example, 50,000 is the region 1, more than is the region 2. So this is and then partition by stock code. So we will define some number, and we will assign some key number to do partition and then print it. But our main concentration would be in the data frame. If you see on the data frame, what we will do here, we will, apply Spark SQL as a general Spark, fundamental and unified data abstraction of Spark. So we need to bring 2, classes, when and column. So COL. So in that case, we will load, data frame. We already done this part. But before we do, now we are going to partition based on the stock code. We need stock code is not integer. We are going to do define some range number. So we want to define this range number, right? To do so, we need to convert it to integer. So to convert integer, we used a cast function. Just add the integer, and we created one field stock code integer. After conversion stock to integer, then we will create new column, because it is going to a stock range. We will call region. So we want to define this region from which to which is so for that one, after where is that convert to integer. So we define the region based on the country and stock code. That is integration of both. So we will say, okay, hey, you need to create a region when, if the field of country is the USA, then if the stock code, this is same as a stock integer, means a stock code. Between this number, 10,002 to 50,000, so we are going to 10,000 to 50. We are saying when this is happen, then you call it North American, partition 1. And then for another one is partition 2, partition data center, North American data center partition 2, partition 1 for Europe. So we will define, and to just show the result, we use the filter. And this is the partition based on the region, because we already created region here. So for a country, we use region. So here, no way we combine two fields, not just play with the stock code. We play based on the country, based on the country condition, and then with stock code. But when we come only country, region is enough, then print it. Some of you later consider that in the partitioning step, we should not use some action. Maybe some of you ask, if you little bit study transformation, filters transformation should not be in the partitioning. But here we can remove this one, not run this one, only this part. But this is, we are going to make sure already every data in that. So that's why we use filter, which is transformation for step 5. We use this, but in the practically, very difficult to divide it step 4, step 5. But if you don't want to use this, you can use this code. This, if you use based on the partitioning only defined, you don't use the filter. That would be okay. In the data set, just quickly show, actually we are not going to deal with that one. You need again name tuple. We already did. Convert the data frame to data set based on the country. You use some filter, and you use based on the range, you define something. So data set somehow is easier. So because you don't need to define this one, only you need to define this and then this. So we already explained about the partition and cluster. So let's do here. We need to do this one to see the partition result. Let's put here. So we don't need this one because this is the explanation. We can put as a comment, no problem, but we can put, oops, sorry. So we can, if we want to keep it, we can make it as a comment. Then we can bring also this one, put here. Sorry. Yeah, let's put this one. And even we don't need load because we already loaded in upper part. So yes, run it. Partition by stock range and region. We already for data frame 4 partition created. That's great. Let's continue for step 5. Okay, step 5. Apply transformation. So transformation, remember, driver has a 2 part, transformation and action. Now is a time for apply transformation. See, here is a transformation for data abstraction. Now is a time in step 5 we do transformation. Transformation operation create, the data abstraction. We will do some map filter. In the action, we will do some collect and counting. So in the transformation, if you see here, step 5, add transformation. So here, as you see, data movement until step 8, nothing happened. So still we are in the, we will not do any processing until trigger, means action. We are now defined transformation, means still logical, conceptual. So driver to cluster, metadata, driver, logical plan, we are in the logical plan. So until logical plan, then when we go to the executor from generating the physical plan, step 7, we are now step 5. So here, step 5, apply transformation. We are still in the logical plan. We are not from step 8. We try to generate, generate the physical plan. So I am just using the mini sort of table to let you deeply understand the practical part. The way I'm explaining, I spent too much time to prepare such a hands-on exercise. If you see in the YouTube everywhere, many books, many classes, many YouTube, Udemy, other thing, they just go to something they don't deeply explain. But the way I'm explaining is, it seems including many exercise, assignment, you can pause and answer my question. Even though if I don't ask you, please pause the video, you can pause and answer, because the way I'm explaining, one time you watch, even if you don't touch practical part, if you don't run on the Google Colab, you easily will understand the concept of the Spark in the the big data process. So let's dive into step 5, applied transformations. So transformation create a new data abstraction without execution, job immediately. Just create a new data abstraction. Okay, transformation in Spark create the new RDD and data frame and dataset. Why? It may some of you ask question, why new? Can you tell me? Please pause the video. Why we need to create new? We already created many times. One time at the beginning for loaded data, second time for partitioning. Again, we created the data abstraction. Here we again created for applying transformation. We create new data abstraction. So far 3 data abstraction created. Why? So before answer this question, let me explain about the concept of the lazy evaluation. Execution defined when you created data abstraction and transformation, it will mean not done until some action happen. So we have a 2 transformation. Narrow one, data proceed with each partition. This is a narrow transformation like filter map. Sometimes wide transformation, data shuffle, means transfer across partition. Here only one partition, but here is many partitions. For example, like we already defined several partition. You may remember here. So partition 1, in the narrow transform, only create transform for one. But for the wide one, between several partition, data, transformation can shuffle and data can shuffle. So let's continue step 5. So real-time connection, narrow transfer. For example, employee in the UK, filter sale data from, UK. This is only narrow. But in the wide one, sales data is grouped by stock code, aggregate from several categories. Shuffling happened to the group sales, for example, between UK and USA. So let's before see the code, let's answer my question. Why new? So if you look at here in the transformation in the data frame, no, not here. Let's I put here some explanation. So why does Spark create multi-data abstraction across different steps? This was the question, right? Because of, one time we create initial data abstraction. Another time when we created partitioning, create data abstraction. Again, in the apply transformation step 5, we create data abstraction. Why? Because initial data abstraction for loading and defining the schema, we create initial, use the either RDD, data frame, or dataset. This abstraction represent raw data and just be a structure there. Why we don't use it? Because of Spark regulation. Spark said, Spark core principle, immutable data abstraction. Every transformation generated new immutable abstraction. And why Spark did this? Because big data, ensuring original data remain unchanged. This design simplify fault tolerance. This is intentionally they again created. Allow for the linkage tracking. So also, and another reason because of lazy evaluation. Transformation are only recorded in the execution plan until an action trigger. So this help optimal query execution in the big data. So since we want to keep it and we don't want to change it, so every step we created new. This is the answer. For example, this is when you filter a data frame in the step 5, Spark create new data frame that including filter data, but this is the point, but does not execute that filter immediately. Keep it. Similarly, when you partition data in step 4, a new partition abstraction are created, but execution not happen. We got execution until step 8. So purpose of this abstraction, because intermediate steps in the processing, optimize opportunities for better transaction, fault tolerance. So if you see example in the abstract using, we load data in the data frame at the step 3, I guess, or 2, I guess, loading, right? So loading was, where was that? Yes, loading is step 3, right? So where is your hands on? Here, apply filter to create filter for transformation. In the step 5, we need filter df. In the partition, we create partition df. When we use df data frames, we created abstraction. So in the summary, you create data frame multi times because transformation, including filter map, create new immutable abstraction without altering the original one, because the rules. And Spark used this abstraction to build an execution plan, ensuring optimization and fault tolerance, because structure of Spark. Okay, let's come to the code. So here for transformation, here this is for RDD load. Here we use the filter based on UK France, and then map, filter map. This is for wide one, for narrow one, only during one partition. But here during 2 partition. But our main code is here. Load data, okay. We need to do filter. For example, country, UK, and then France. We want to filter during one partition. So we need to choose a specific stock, code, either by name of country or stock code. But here between partition, group by or aggregate. So we need to define some library. So we will do aggregate and group by based on the stock code. And so this is the one example for group by stock code. For data set, again, here we already did, we need to convert. So for data set also we need to do first data frame, and then like UK, we need to use filter based on which country we want, and group by, we need to do grouping based on the, for example, group all sales by stock code. And this is little bit complicated because we are using the group by reduce and map together. So what we need to only focus to this part. So narrow and wide transformation. So let's see the result. So here just we need to put comment for here, and here comment for this one. Let's make it bigger. See, same code. We just want to ask for showing just 5 for based on the stock, and based on this is the wide result 5, and for narrow this is the narrow 5. So 5 for narrow, and for the narrow one we did one time based on the country and based on stock code. So 2 table for the narrow, 1 table for wide one. I think everything great. Yes, so already 5 showing, so we already integrated within 1, and this is within 2. This is aggregation for stock code. Okay, successfully done until here. Let's continue. Okay, now we reach to step 6, tag. So this tag is the directed acyclic graph, which we already talked about that. In step 6 and step 7, if we come back to our graph, so in step 6 here and step 7, tag creation means logical plan creation. Until here, we didn't create logical plan. So when we reach to the step 6, logical plan created, and then step 7 logical plan optimized. In the step 8, physical plan generated. So step step 6, and step 8 is very important for us because logical plan here created in the step 8 physical plan created. And if you see here, until here, we didn't do anything let's go another page. Yeah, this page. You will see here in the step 7, until step here, no data movement. So until step 7, when we physical created step 8, shuffling if needed we will do, and then data processing here. Until here, we just thinking, designing. So consider, DAG is now a graph. We design graph all transformation and all classes, function, all relation between each clusters. We are going finally design until here. So now you got the point. Let's back to the slide. So is a logical representation and will be applied to the data, is a backbone of the execution model because it's a logical plan is created. So that is very important to consider. Here logical plan will be created. Helps for visualization and linkage of the transformation. Transformation already create in previous steps. Here we will show it. And transformation build a DAG but are not executed. So that transformation, when we create it, we will make it, but we will not until action is triggered. So DAG for our real life connection for regional states means filter select data from the North American data center or European data center. We select the data by filter. By map, calculate the total cell for each stock code. Reduce group, something like that. This is the a narrow transformation. This is the wide transformation. So in the North American data center, DAG filters data for USA and Canada, partition 1 and 2. And EU, this is the parallel execution for data center. So let's see on the code. This is the RDD, load data. Here apply transformation. So you will see the filter and map. And just view the DAG using the logical plan. But here, for data frame, load data here, we will use same call here, apply we already, and then we will use logical plan by calling explain. So this is important. So main is here for DAG is the explain, and so that makes us. But in the RDD we just use the to debug string. So mainly, and here this is conversion. Okay, apply to convert the data to data frame, and we will use here finally also explain, but procedure little different from map. But our main task would be here. So let's bring to our main code. So you see, this is the graphical part showing this is the physical plan, mean our plan. This is the DAG. DAG is this. So DAG is like everyone is a node and then connected. This is connected together, showing by this one. And you can see for instance, when you file scan, start from here, then you do filter project. So this is maybe difficult for you. Get the point. You can also use graphical showing. For graphical showing, actually, here, okay, if you just some point before graphical I show, DAG in the RDD used to be a string to view linkage between transformer, right? But in the DAG, in the data frame, use the explain. So this is the, and dataset same. So showing the, logical plan. So advanced, DAG, we can use visualization or using the Spark UI to show that one. For our region, filter and maps, means for North American, and then we need to process European data, aggregate, and this is explained in the code. So for advanced one, just this is optional. Actually, this is DAG, so for sure you don't need to worry. That's finished this part. But since I want to show you some graphical, you will see matplotlibs. We already use it, and networks NX using the DI graph to show based on add node. So G add node, which one? This one, add node this one, add node this one, add node this one. So you can add node everyone and then add the edge connection between these two together. So filter and project. Connect the filter and project, these two as an edge. So simply use it and then draw by a function like draw. This is the setting, color, black, size is nothing much difficult. So this is optional. This is not main. This is additional, just I want to show you. But if you don't use it, it's okay. You don't need to worry about. So this is already matplotlibs. This is using. This bring all of this graphically. Node and edge is nothing difficult. And you use the just figure matplotlibs and just simple draw. This one you can change it, font size, everything, and just show it. Okay. Wow, here you are. Great, good job. So you see, this is the file scan here. Then come to the filter, and then project and hash aggregate, and then exchange here to here. So this is the Spark DataFrame transformation DAG. This is the logical plan. Without this, also this is understandable, nothing difficult. So let's continue. So in the step 7, as I said, is a logical plan optimization. So in the DAG, scheduler, you need to optimize your logical plan. For instance, divides logical plan into narrow and wide, optimized by combining narrow transformation into single stage to reduce overload, reduce data shuffling by reordering stage and optimization. So here, Catalyst Optimizer enhanced data frame and dataset. So in that case, we will use predict, push down, filter every data. This is just a projection. Try to that graph getting better shape. Catalyst optimization we don't have in the RDD, so it doesn't work. So for this one, okay, you may ask what is the real meaning of the Catalyst optimizer. Actually, here we are ending the logical plan. Step 8, physical plan will be started. So Catalyst optimizer is something between logical plan and physical plan, and make it ready to go for physical plan, and makes doing memory management better, and reorganizing, joint and minimizing, shuffling. So let me explain more, especially Catalyst optimizer, predictive pushdown or projection, pruning or joint reordering. What does it mean? I'm going to explain. So let's I add some part to explain. Catalyst optimizer work by applying several optimization technique to transfer, logical plan and what we really need in the logical plan. Many times I'm repeating. Physical plan, how it will be done. This works for only data frame and dataset, not RDD. So what is the predictive predicate that push down? This move filters closer to data source, like where clause. So reduce amount of data read to the memory. So memory is important for Spark, so managed for that one. For example, in our case, if the filter country to include only US and Canada, Spark push the filter down to the data source. So only relevant rows are fetched, not other row for other column. So for example, here I can give in the real connection. For example, for predicate, a query like filter in USA cells benefit from this push down function, which ensure only rows related USA Canada are read. So calculating total cell for this country benefit from the projection at only a stock country and quantity, not the other. So these two can be done. So here projection we already explained, the select the necessary for column computation, avoid loading processing data. So for example, if your query use a stock or country field, Spark avoid loading unrelated column like invoice data. So joint reordering, this is a reorder join operation to minimize size of the data. So the relation to the DAG scheduler, what is the Catalyst optimizer? This is hands in hands with the DAG, because Catalyst optimizer focuses on logical optimization, like using the several functions to improve the query performance. DAG scheduler focus for splitting, optimizing logical plan to the stage and scheduling tasks to minimize shuffling. So this doesn't work for RDD. So let's go for code. What is the code? What we are talking? We are talking about DAG scheduler. Means we are going to optimize logical plan. So here, same as before, apply. So here we just use same function to optimize in AG, because there is no optimizer in the RDD. We cannot do anything. But for DataFrame, so Catalyst optimizer apply optimization. These two we will going to use it. So we will use those tools to optimize that are, you can see here, same code, only because this is internally, this predicate, push down, and projection pruning, this is implicitly happen. The difference only here, the true here. So let's run this code. You see here we have only true, but previous one we doesn't have a true. So you will see optimized DAG. Here is different. Wow. Now this is optimized. So analyze logical plan, optimize logical plan, physical plan. Now this DAG is much optimized than this one. So and also we can use this is for data set. So here also same, only true. So this is the what this we can show, we cannot show, but if you want I can show it. Same thing, same function, using that one to show better. So this is much better. So if you see the difference between this is a start from file scan, go here. For instance, here is the filter projection, but here is different, customize it to the project filter. So to see the difference, so what is different logical and optimized plan to understand in the DAG. So this figure, it shows, this table shows very nice to compare the code first, which is step 6 and step 7. In the logical plan, level of abstraction is a high level, but when we use that true one, go low level, incorporate physical execution, because it's close to the step 8 is a physical. Here is a logical high level. Partitioning does not explicitly include partitioning, but we will see the exchange here. You can see the exchange here. And here you have a hash aggregate partial sum. This is the hash aggregate partial final. So this is hash aggregate partial final, but this one is the hash aggregate sum. So the aggregation shows basic group in the logical. When you optimize it, optimize grouping with the two-step processing to reduce data shuffling. Node naming difference, you can see here file scan, but you will see the different name here. For example, here file scan, here is the relation, and physical, nothing here, start physically, hash partitioning, and purpose show the logical flow, but here executing flow. This is the big difference. Okay, for step 8, let's dive into main concept of data shuffling and physical plan generation. So let's see our table. We reach to the step 8. We generate the physical plan. Still, if shuffling required, we will do. Processing not happen. Driver cluster management. Talk with the cluster management from now on. So you remember here, we talk about the cluster management here. Cluster management. So step 8, now everything was a logical plan. No talking with a cluster here. When talk step 8 start means physical plan will be started. Right? So this is the important point here. And for step 8 here, you see that logical plan is optimized like here, but generation of the physical plan start. When step 9 action done. Before action, you need to create a physical plan. This is the point. So shuffling means redistribution of data across the partition during the wide transformation, because narrow transformation no between the partition. Only wide transformation between partition happen. Expensive due to disk I/O and network communication, because some shuffling happen. So data, physical plan generation. So this is, we already explained this one in the table. So a strategy to minimize shuffling, broadcast a smaller dataset to all node, avoid shuffling, or tuning partition, adjust number of the partition, which you can do it. So this is through the broadcast. This is the partition can manage it. So the redistribution, this is our example. Cells, data across the partition to group cells by, stock code. And this is redistribution already. Let's go to the code. So this is the RDD is here, just minimize shuffling. This is the new part, using the, map partitions and using get number partition to control the number of partition. But for here, what we have to do here, this is that we already had wide transformation. So we need to minimize shuffling. So broadcast join. So here we will define one more, data abstraction here to do, join between these two and then print it. This is, since our partitions is for good enough, so nothing changed. We just broadcast this one. This broadcast between the driver and, executor. So let's run this one. This is step 8. So we will see the result of, here we use the minimize shuffling, create, data frame, and then we use it join, and then we use this tag explain here as a result of the total sales. Total sales for what? For different categories and stock. Based on the aggregation, we did group sales by stock code. So this is the between two. So this is really ready to do some action. Let's dive into step 9. Apply action. Action in Spark trigger. So main things happen: execution of DAG. DAG until step 7, it was just logical, and we will execute DAG and return result to driver, because step 8 we start to talk with the cluster manager, but we will run the DAG. The result will be, for example, counting rows, collecting data, something like that. Lazy Spark, means we create the DAG transformation until level 7, but does not execute it until that's what they call slow. They call lazy. So simple action perform the step forward like count or collect. Complicated, we can use reduce or for each function. For example, here calculate total sale record USA and total sale quantity for Canada, and then aggregate sale for UK, count sale for other European country. So here in the RDD, you just use count or take some as a sample, because this is the unstructured data. This is for some simple one, and this is for complex one. So here using map several data, and or using the for each for that. This is for RDD, but for our main data frame, we use action count, but for complex one we try to use aggregate through the aggregate and then collect. So as here explained, we use the aggregate and then counting. This is just to use total calculation of the USA. So here same conversion using just simple action. We use the DS count, and for complex one use the map. So let's do it for do action. So we need to put comment here, and for this one, because this is not part of code, and then run it. Yes, so we already total rows will be returned to the collect, and we did some action and process done. This here until step 8 after physical, going here aggregate total cost USA and Europe back to the driver. In the action happened. So it was several steps done, nothing happened. So that's why this is lazy evaluation. This is the main point of the big data. Not too many transactions between the user and data and server. Less until they need that is happen. So you can see here the result come to the driver. Okay, almost finish. Well done. Let's finish 3 more simple part. We need now our result finish. We want to export the result and store in our external data. For example, the user here did transaction, wants to store result of the big data process. So here can use any format like CSV, Parquet, JSON. You can save. And here's let's simply go. This is similar. For example, for RDD you can, but let's go for our main. So let's save in the CSV and Parquet, 2 different. So let me copy paste and show and explain on the Google Colab. So let me, it will be saved here. Please pay attention. We are trying to load data, okay, and then group by stock and calculate total score. We already did, and we are going to save results. For example, for New York data center. So in that case, we can have output. For example, in the New York data center, saying from, you remember 10,000 to 50 is for New York. If you do this content, it will be saved in the Google Colab. But if you want to see here, it would be better. You can do it. This is also possible. Okay, let's run it. So you will see here will be created one for USA output. Yes, one is the Canada output. This is based on the CSV, and Parquet format using the France output. This is data is a Parquet. This Canada output. This is the CSV. For instance, if you download it, so this is the result total sale of the Canada. Very nice. During that range we defined total sale, and for USA was here. You can see the USA is the CSV file. This is the for USA total sales aggregation, and for Parquet is a format, another format. So for instance, for the UK, France, you can download Parquet, but Parquet you cannot see. You need to Parquet view. I prepare one Parquet view to show you. For example, this is the view Parquet, data converter to the Parquet. If you run it, data converter.io view Parquet, so you can see your download. In the download, this Parquet, if you see, you will see the result in the Parquet. You can export in any other format. So this is the Parquet for UK. So good job. So as you see here, we already done exporting, including logical and physical. So in the we are step 10. Now write to external. Load processing already done. We are driver to storage. But before, until here between driver and cluster. But here from now on, you can locally do, we can do optimization now. Let's do 2 more steps and finish this hands-on very nice exercise. So store intermediate in step 11, optimize workflow. In the memory we want to keep the data in the memory for fast during the repetitive computation. So you want to save, intermediate result to a stable storage for fault tolerance to break the linkage of transformation. For example, cache intermediate result to optimize query repeating. So then simply for RDD is a cache. Also here this is same loading filtering. Just simply we use cache. That's all. Then we bring data to the cache, and we also set a checkpoint to check directory. So for converting it to the RDD. There is a 2 thing. Caching and checkpointing. The difference, caching we bring to the memory for fast accessing for short term, but checkpointing for long term, and we control fault tolerance. So here I put some point. Caching speed up repetitive queries by storing intermediate result in memory, either for temporary reuse of result because it is in memory. Checkpoint save result to the disk to have for long term. Break the linkage of transformation to ensure fault tolerance. We can also combine 2. Use caching for quick access, use checkpoint for long-term fault tolerance. So let's do in the code. So we need to put here caching and checkpointing. Yes, great. So we try to, total records as a checkpoint completed, and we put in the cache all information, stock information to increase the speed. So we already used the cache, driver optimize plan, reduce the redundant and movement. Now we need to monitor executor for driving. We can do some visualization like we did before. This is optional. To see the result, I will show on the code. So this is, you already see the DAG final result. So if you want a better understanding the result, so this is same using the Matplotlib PLT used at the node and edge. This node and edge, this is the optimized one, and just run it. Yeah, well done. This is the Apache Spark DataFrame transformation DAG for logical and physical. This is the having the exchange, both logical, physical would be here. So well done. Yeah, I think we already reached to the end of the hands-on exercise. Just quickly recap what we did. We start from until here. It was the physical part. Sorry, it was logical part, and then here the physical part. So until here, there is no connection between driver and executor. So preparation, many things inside. Main thing, it was transformation and actions. Trigger the action, it was trigger the execution. This is the action. You can see in here. Yeah, here you see the action in the step 9. Transformation here. The concept of big data is a lazy evaluation. So you saw how we try to do every process through the hands-on exercise. So the reason I explain a lot because this is a little bit complicated, but the way I explain it was very, straightforward. You see by view code, you can make a data center and control it through this is the real big data. I hope you enjoy this project, and through this hands-on exercise, I wish you learn many things here. Let me recap. Initialize, then we create data model in the step 2, 3, 4, and then apply transformation DAG creation and data shuffling and physical plan generation. Step 9 and 10, apply action and doing save and export. The last part was optimize work plan and job, debugging. And yeah, that's all. So believe me that I spent too much time to prepare this very great project, full A to Z, real big data. Because I was thinking only pure theoretical, it will not help you to understand the concept of big data. But through this project, this hands-on exercise, simply, easily, nicely, professionally, I try, let you learn and bring you to the new era of big data. Who really pay attention to this hands-on exercise will understand the value of this hands-on practice and exercise. And we already covered AI and big data. We did many things theoretically, practically for AI, combination of AI and big data. And this last one was wonderful. Although it was very difficult, prepare such a huge, several months it took to prepare very nice hands-on exercise. But what I believe, this will be, this sort of lecture and lab lecture will be open your mind for future. And I believe you will be a great engineer, doctor, professor in the company, in the university, and I will proud of all of you. Thank you very much.